Okay, so our plan today, after building up some introduction to the real numbers, is to begin to count sets of real numbers. And in order to do that, we have to lay a groundwork for the idea of counting. So that's our plan for today. We want to talk about how to count. And as you saw in the Sesame Street video, why is it that we bother to count, and how is it that we count? So here's a question. If I wanted to, for instance, count a bunch of fish, well, if I weren't going to use a number to describe how many fish I had, I might do like the figure in Sesame Street. Fish, 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 fish. Okay. But there's a problem with that, and that is it actually is kind of hard if you have 52 fish to count to actually list them all out, right? So we have a way of doing what? What is it we're doing when we count? What is it we're doing? So for instance, if I count the number of people in the first row, I'm saying 1, 2, 3, 4, 5, 6, right? Fish, 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 right? Or if I'm a little baby just learning how to count, and I want to count the number of toes I have, I might be in my crib, something like this, and I'd go 1, 2, 3, 4, 5. Okay, what am I doing when I count? What is it that I'm doing? Yes?
You're assigning a number to each object.
I'm assigning a number to each object, yeah. And in fact, what kind of number? Is it a number like pi? Oh, a natural number. Okay. 1, 2, 3, 4, 5, 6. Yes? Okay. Now, if you asked me to count the number of people in the first row, and I counted like this, 1, 2, 3, and stopped, would you be happy with the way I counted? No. Why not? Because you weren't somehow included, right? Okay. What if I counted like this? 1, 2, 3, 4, 5, 6, 7, 8. Well, Paul is happy. He got counted twice, but you're not happy with that as a method of counting either, are you? Right? Yeah. So we're mapping the items, the people in the first row, onto the natural numbers, right? And that's in fact described formally by a function. Excellent. So the first thing we have to do is we have to talk about or ask people to remind themselves about functions. Okay? So often we denote a function like this, f colon a arrow b, and this is to signify that a is getting mapped onto b. So you have a picture that, might look something like this. Here's a, and here's b, and here's a function, f, that we like to say maps one thing onto another thing, okay? Or into another thing, not necessarily hitting everything. We say maps, that's one way to say it. Another way to say it is it associates to each little x an element f of little x in B, if x is in A. So here you might have a point x, and here is the point f of x. And it is a function if for anytime you put in the number x, you get a unique thing out, right? It's not like you could put in x many different times and get different things depending on what time you put x into this function. Okay, so there's a unique output for each input. Okay, but it is possible, for instance, that there might be several points that get mapped to the same point, right? It's possible that maybe x, but also y gets mapped into this one point, okay? So it's, this has the property that 2 points might get mapped to 1 point, okay? And so there's at least a place here where it's 2 to 1 in some sense, okay? Okay, so very good. What else? Maybe I should remind you what we call A. A is called the something of the function, the domain of the function. Yes? Ring a bell? And B is called the? No, it's not the range. Thank you. It's the codomain. The distinction is the range is only the things that actually get hit. Okay? So we should probably mention a few other terms here. We should say that, let's define what we mean by F. Okay, so if, let's say you have a set C in A, and you have a set D in B, so C might be some set over here. So, you know, maybe C is like some funny set here, right? Maybe C is like this. Okay, just, it could be disconnected set, no necessary reason it has to be connected. Then we'll define F of big C to be basically the image of C under this mapping. So we would say all F of little x, where x is in what? C. Okay? So this has a name. It's called the image of C. And where does it live? Lives in B, lives in B, right? So the image of C, these two blobs might get mapped onto the same blob, right? So if this is C, then this would be F of C. Happy? Okay. Okay, great. And then we can also define a corresponding notion of, if you're starting with a set here, there's sort of a way to go backwards. So, you know, maybe, let's say I start with a set over here. And it gets, what's the corresponding notion? So maybe I'll call this set D. What's the corresponding notion if I want to somehow bring it back over here and look at the points, some special points over here related to the points there? Well, not surprisingly, you might look at, call this thing the inverse image. So this is the image of C, and this is the inverse image of D, which is in B. And it might define it to be, here's the notation, F, you write a little -1 to indicate you're going backwards. It's the inverse, if you, in some sense, okay? And it's the set of all points over here that get mapped into D. Are you with me? So I might write that as the set of all little x such that F of little x is in D. Happy? Comma? The inverse image of D. And so that over here might look like this. Right? Okay. Happy? Okay. Now, again, what I want to point out is if you have some points here, maybe a single point in D, it might have multiple preimages. Right? Multiple points, right? Okay. So many things can get sent to one thing. That is why the inverse image is not necessarily a function, right? Because you take one point here, there's no way to say what unique point it's associated in the opposite direction. Yes? Okay. But there is a situation in which we can talk about an inverse function. So let's make some notation then, some definitions. So we're going to, there's a very special situation where suppose the range, so if f of when f of a, if you take the image of all of a and it hits all of b, this is a situation where the codomain is the range of this function. The range is f of a. So this is the range. It's the image of everything in A. When the range is all the codomain, then we say that f is onto. It's an onto function. There's another word that was actually popularized by a group of French mathematicians. We say it's a surjection. Or if you're French, you might say surjection. Okay? Sur, of course, means what? On, right? On or upon. So it hits everything. It's a surjection. Surjection is a noun. Onto is a adjective, right? You call a function an onto function. Okay? You can make this an adjective by calling f surjective, right? Surjective, right? Okay, good. What else? Well, let's see. That's when you hit everything, and now if it never has multiple points getting sent to one point, we'll say it's one-to-one. And there's another way to say that, is if the image of 2 points being equal implies that x and y are in fact equal, we'll say f is 1-to-1. We have a special, there's another name word we might associate to f. We'll say f is not a surjection, but an injection. Injection. Right? Okay. Okay. So this is another way of saying it only sends 1 point to 1 point. If the image of 2 points is the same, those 2 points have to be equal. Okay? You happy with that? Another way of saying a function is an injection is if the inverse image of a single point is a single point, right? Yeah, and you could, in fact, define a function that way. Great. So when both these things are true, when f is 1-to-1 and onto, we call f a bijection, right? A bijection. Happy with that? Okay. These are all terms that come up quite a bit. We have a notation that sometimes can be useful as shorthand, not in formal writing, but just as shorthand. For surjection, we often write the arrow with a double arrow at the end. For injection, we imagine a little hook here. Okay. And a bijection is sometimes in shorthand written with both the hook and the double pointer. Okay. Happy with that? Okay. So that's just to get a little bit of terminology out of the way. If you have a bijection, then this bijection, notice, is a function that will, in fact, whose inverse is also a function, right? You can talk about the inverse of f. It will have everything as its domain, which is what you want, and it will send something over here to a unique thing over here, right? And the problem with some of my counting methods earlier is that you weren't happy unless this function were a bijection, right? If I said 1, 2, 3, well, that's a function that's not what? Onto. And if I said 1, 2, 3, 4, 5, 6, 7, I counted you more than once. It's not what? 1-to-1. It's not a 1-to-1 function from the numbers 1 through 6 to the numbers to the people in the first row. You guys are more than just numbers to me. Okay. Great. So we call f a bijection, and in fact, and we say that A and B are in 1-to-1 correspondence. This is a big term. 1-to-1 correspondence. Okay. we might also write A tilde B. It's not terribly standard notation, but in our context, in our book, we will shorthand A and B are in one-to-one correspondence by using a little tilde. Okay. Okay. So, what's the point of one-to-one correspondences? Well, it's basically saying that, if you like, the number of things in one set is the same as the number of things in the other, if I haven't even defined the word number, but in some sense they have the same number of things because I can associate in a one-to-one way a number, or a point in A with a point in B. Okay? And in our case, when we count 1, 2, 3, 4, 5, 6, what am I using for the set A? Natural numbers or some subset of them, right? The first portion. Okay? Okay, so what do I mean by counting? Well, I'm just going to refer to this as elementary counting. I am using, as one of my subsets, a set which I'll call J sub n, which I'm going to use to mean 1 through n, a subset of the natural numbers. Okay? That's what elementary counting is doing, is associating 1 through 6 with the people in the first row. Everybody happy with this? Isn't this, in fact, what we do when we count? Isn't this what a baby does when she's counting the number of toes on her foot, right? 1, 2, 3, 4, 5, right? Yes? Okay. Good. Well, we have a very nice way now of associating numbers, natural numbers anyways, with somehow the notion of size of a set. Okay? So now, if you give me a set, I can count it. How can I count it? Well, here's a set. Maybe it contains a number 1, maybe it contains a smiley, cyclops smiley, a double smiley, and the number pi. This is a set. Okay? And can I count the things in this set? Sure. I could count them in many ways. Of course, the one way you normally think about counting this is 1, 2, 3, 4, yes? But there's nothing stopping me from associating with my function, counting them in this order, is there? Right? So what I'm doing is I'm associating to J4 this function that corresponds to whatever the set is called. Maybe I'll call this set A. I'm associating to a set one of these initial segments of the natural numbers. Okay? Happy with that, Daniel? Okay. Okay. Well, we've made a start here. Let's so if I wanted to talk about the size of A, I might say that the size of A, which I will denote by an absolute value, here's the symbol we sometimes use, is in this case what? 4. Okay? Interesting. Okay, interesting. So, that's kind of cool. Is it possible to associate to every set a number, a natural number, in this way? Well, there's a question. There's an interesting question, right? I mean, for instance, if I look at the numbers, if I look at this set, well, first of all, is this definition even well defined? You hope it be well defined, but it's not clear from the definition. The definition was, find me a one-to-one correspondence with a subset of of the natural numbers, the initial segments, right? But how do you know that there isn't some other one-to-one correspondence in which I get 5 by the time I'm done? There's a question. Would you agree that's a question? That maybe we might need to worry about, yeah? And even if you settle that question, then I guess another question is, are there sets for which it's not possible to find a one-to-one correspondence with some subset of the natural, can't say the word finite yet, with some initial segment of the natural numbers, okay? And if you can find a association, we will call such sets finite. So here's a definition, which it's not clear we'll need yet, but let's make it. We will call a set finite if what? Well, if A can be put in one-to-one correspondence with one of these initial segments of the natural numbers. We sometimes, by the way, let me add one thing here. We sometimes associate A with the empty set, which I'll call J0, which is the empty set, and then that will solve this definition as well. We'll call A finite if this is true. Everybody happy with that? And else, we'll call A what? Infinite. Hey, that's great. Okay, it's our first occurrence of a formal definition of the word infinite. Yes, question? Why did I use the letter J? Just to agree with the book's notation. Yeah. I think the book uses notation. It's common because I's can sometimes can be confused with lots of things, but J's, it's just another letter. Okay, great. Are there any infinite sets? Can you think of an infinite set or a set that you might suspect of being infinite? Oh, just throw out some ideas. Natural numbers? Are they infinite? If you look at the book actually doesn't settle this question, but we'll settle this question. Well, the book actually assumes that, in fact, n is infinite, but we'll see why it's true in just a second. Well, let's explore a few things about n. So there's a special situation where you might worry about one-to-one correspondences, and that is in the case where you have A equal to n. So it's no longer elementary counting. It's counting using all the natural numbers. Haven't yet established if if the natural numbers are infinite, but let's go ahead and make a special definition. We'll call A countable if A can be put into one-to-one correspondence with the natural numbers. Okay, and one question you might ask yourself is there any difference between these definitions? Okay, very good. So let's just see what things are countable first of all. Okay, so here's an example. Let's see. Would you say the natural numbers themselves are countable? Yes. Good. And if you say that something is countable, you have to give me the bijection that achieves that claim. What bijection would you use between the natural numbers and itself? So this is n going to n, and I'm claiming that n is countable, and what that means is I can find a bijection between the natural numbers and the set n, that one, right? So use this where what? F of little n is what? Itself. Okay, that's very easy. That was not hard. And itself is countable. Love that. Okay, here's another example where you might, very common example. Let's look at a sequence. So the sequence here is x1, x2, x3, just some sequence, dot, 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 meaning keep going. Is this, and let's say these are distinct terms of distinct terms. Would you say this is countable as a set, a sequence? Yes? Why? Yeah, set up a bijection taking a number to the nth number to the nth thing, right? So you think of it this way. This is the first thing, that's the second thing, that's the third thing, etc. And this is the bijection, yes? If I want to write it, however, I'd write it like this. Oh, I probably should not have used the same color because it's really this n that's associated with the number. And in this case here, sorry, that was from the earlier example, but here I'm associating to the natural number 1, the nth thing. So maybe I'll write it like this. Use f of little n as xn. And what this does is it provides so this provides a function from n into the set x sub I as a set. Okay? Everybody happy with that? A bijection. Now, the thing I want you to notice is any sequence that's indexed by the natural numbers is countable, almost by definition, almost because you can see what the bijection is. And so the moral of this story is, if you have a set of numbers that can be, or a set of objects that can be listed, it's countable. Listed in a sequence is countable. And I'm abbreviating countable now. Okay? It's a very, very helpful insight. So let's do some other examples then. You can see what else has to be countable. Would you say this sequence, starting at 2, is countable? Yes or no? Yes. I don't even have to write it down, but I will. What is the bijection? Use f of n equals n plus 1. Excellent. Okay. What about this set? How about the set that starts at 1 and goes up through, let's say, the kth element, but skips it? So k minus 1 goes to k plus 1, k plus 2, and then continues. Is this countable? Yes. Is. I won't rewrite countable, but it is. Okay. What's the bijection? Now, at some point, I'm just going to force myself to write it now, but once you have this fact, you don't need to explicitly write down the bijection, but let's do it. What bijection am I going to use? Let f of n be n if n is less than k. Good. And let's let f of n be what? N plus 1 if n is greater than or equal to k. And the reason I'm putting equal in is because this is the natural numbers, and now on this side you're skipping the kth thing, right? You happy with that? Okay, now, would you agree that if I can see the listing, you can, if someone forced you, write down the bijection? But we won't, it won't always do this. I'm just going to do this now, okay, just to help us out. Ah, very, very good. Okay, so I claim now we have just enough to see that, in fact, a countable set is not finite. Okay, this is not in the book, but I'm doing it for your edification, because you might wonder, theorem, n is, or any countable set, is, in fact, infinite. Okay. How are we going to show this? How are we going to show this? How do you know, for instance, that Harris doesn't have a secret one-to-one correspondence of n with some finite set that I just don't know about? Right? Maybe he's discovered something that none of us has discovered. How are you going to rule that out? Yes? Oh, sorry. Go ahead. Okay. So your idea is to say that somehow for any natural number there's always a bigger one? Okay. What do you mean by that? They never stop. I mean, how do you know? So it's certainly true with the ordering that we normally think of, like you write them in order 1, 2, 3, 4, 5. That's a particular correspondence of the natural numbers with themselves, right? But how do you know there isn't a secret one that Harris has that nobody else has, that in fact associates to any number way over there some number over here? Here's a question. Okay, so it's a harder problem than you might initially think of, but but we can see why it's true now. We have enough to see why it's true, and I claim you can see that maybe in this example here. So let me just sketch a proof. By sketch, I mean I'm not writing out all the details, but enough to show you why it should be plausible. Here's what we're going to do. We're going to prove this, like all good things about the natural numbers. When we have no insight, we're going to prove it by induction. Okay? So here's a proof by induction. What am I going to induct on? What's n? Little n. What's little n? So I'll just tell the reader first. I'll say, well, we'll do it on little n and show what? We'll show that n is not in one-to-one correspondence. There is no bijection between n and j sub little n. Would you be happy with that? Okay. Okay, we'll do a base case. And if you like, would you agree that it's clear, I won't write this down, it's clear that the natural numbers, there's no bijection between the empty set, or even the set with one element, and the natural numbers, right? If you had a one-element set and the natural numbers, then this one thing gets associated with one other thing, which you can remove, and then there's a lot of stuff left over. It can't be onto. Would you agree with that? Okay? So no matter what function you pick, you can see what they all have to be. This one element, so I'll just do the base case here. I'll write out sketch. Base case, let's say if n is bijective with the set 1, but clearly n's not empty. And if it's bijective with the set 1, then what do I know about 1? It gets mapped to somewhere in n, doesn't it? Then consider n. Now, whatever that function is that takes 1 to something, no matter what it is, if you omit that, there's stuff left over. Then n, consider n minus the inverse image of 1. Okay, so I'm going to need to give this a name. Let's draw a little arrow, bijective arrow. In fact, let me draw the, if you don't mind, I'll just draw the bijective arrow backwards. I'll call this function g. Then consider n minus g of 1. It's non-empty. So g is not onto. Or the other way to say it is, if you're looking at the forward function, g could not be 1 to 1 because everything has to get mapped to 1. Right? Lots of ways to see that. Okay, so what's the inductive step? Well, it goes something like this. I'm going to show you that if there were some secret bijection between n and a segment j sub n, then there would be another secret bijection between n and the segment with one less number in it. Okay? That would provide the inductive step because that would show that if there were a bijection between n minus 1, the n minus 1 segment and all of n, then there would be between that and n. So let me just say this. We'll show if j sub n, I'll say it a different way, is bijective with all of n, then j sub n plus 1 is bijective with all of n. Okay, and how are we going to do that? Let's just sketch that a little bit here. We'll do it by contrapositive. So if there were, let's say, a bijection between j sub n plus 1 and n, and let's call this bijection, if you like, let's call it h. I'm going to do this backwards, sorry. N, j sub n plus 1, I'll call it h. This is a bijection. Then what could I do with this? Here's the thing that I want you to notice. I claim I can now construct a bijection between n and j sub n. How will I do that? Well, what's j sub n plus 1? It's the numbers 1 through n and then n plus 1, right? So what's going to happen? Let's do the following. Here's the picture you might have in your head. Let's associate then, in the following way, this picture. So would you agree that under this bijection, n plus 1 gets associated with something over here? Yeah? Okay. What does it get associated with over here? Actually, I probably did want the arrow to go the other way. Here, let me draw it this way because it's the direction that I want. Would you agree that if there were a bijection like this, by removing one thing on both sides, I still have a bijection? So if there were a bijection between all of n to this, then there is a bijection between n minus the set containing h of n plus 1 with what? J sub n. Agreed? Yeah? Oh. Then this would be a bijection. Then there exists a bijection between this and this. Yes? But wait. What about n minus itself? Minus one of its elements? There's a bijection between this and what? and n by the previous example. So I claim also there exists a bijection. Let's give this a name. I'll call this one H prime, or H hat. It's a little nicer. And there's also a bijection, we call it F, by the previous example. That goes between this creature and n. So I have a bijection between this and this and this and this. Therefore, there's a bijection between what? By composing these functions? Between this and this, a bijection. Oh, interesting. And so what I've shown is if there were a secret bijection between jn plus 1 and n, there is one between jn and n, and that is the contrapositive of this statement. Okay, so this statement, we've just established this inductive step. Okay, so the conclusion is there exists a bijection between n and j sub n. And that establishes the inductive step. Okay, Bonnie?
Isn't the contrapositive of JN not bijected with n, then JN's plus 1 not bijected with n?
Sorry. Let's see. So if we want to show that if there were oh, yes, sorry. Thank you. Right, the inductive step is to show that if there is a bijection between n and this, then there's a bijection between n plus 1 and this. Right, so actually maybe I need to, right, I'm not doing the contrapositive. I want to do it directly, and I still want to use a lot of the same ideas. Thank you. But I probably need to construct this differently. Yes. Wait, let me hear what Jenny had to say.
I don't think that's what you wrote down is not what you showed over there. I think you showed if j sub n plus 1 then is the same. It should be jn plus 1 then jn, not the other way around.
And that right, and that is the inductive step we want, right?
Yeah.
Yes, thank you. Okay, right, thank you. Yes, so the comment was, thank you, I've messed this up. The inductive step is jn plus 1 is not, if there were a bijection between n and jn plus 1, then there's a bijection between n and jn. That establishes the inductive step because the claim is there is no such bijection. This is the inductive step that's required. The base case was there is no bijection between the whole thing and 1, and this is now showing if there is no bijection between jn and n, then there wouldn't be one between jn plus 1 and n, and that's established by showing the contrapositive, which shows that jn plus 1, if this occurred, this would occur. Right, thank you, thanks. Yeah, I think I'm just going to leave it like that because this was supposed to be just a sketch. Thank you. Okay, so what's the key idea here? The key idea here is n is infinite, and the way we showed it was it's infinite because it actually can be put into one-to-one correspondence with a subset of itself. Okay, which is actually a very surprising fact that at first blush seems really ridiculous. Right? How can you have a set that in some sense has the same size as a subset, a proper subset of itself? And it turns out that that is actually something that characterizes infinite sets. You can show that infinite sets, a set is infinite if and only if it can be put into one-to-one correspondence with a subset of itself. And we've just seen that here. Perhaps even more dramatically, if I wanted to, I claim I could put n into one-to-one correspondence with the subset of even natural numbers. So how would you do that? Here's the even natural numbers. The even natural numbers here are 2, 4, 6, 8, dot, dot, dot. And what's the correspondence then? What would I associate to a number here? Yeah, f of n equals 2n. So the natural numbers and the even natural numbers have the same size in some sense. Okay? We have a word for this. We use the term cardinality or cardinal number. We say n and 2n have the same cardinality. It's a mathematician's word for size. And what that really means is they can be put into one-to-one correspondence. How many people find that at least a little bit surprising? A little bit. I mean, now when you see it, and of course it's not surprising anymore. Question?
So if n and 2n are both infinite sets,
Yeah.
does it really matter, like, at all that there, for every element in 2n, there's 2 elements in the n set?
So the question was, yes, I believe you, but can't you also say that for every element in n, there are 2 things in here? Is that your question? And the answer is yeah, but the definition of one-to-one correspondence is you just have to find some correspondence between bijection between n and 2n to show that they have the same cardinality. It doesn't preclude the possibility that there could be other mappings that are 2 to 1 or 3 to 1 or n to 1. Okay. Yeah, it's a little strange, right? I mean, I think you're thinking, okay, well, if I look at the numbers 1, 2, 3, 4, 5, 6, 7, 8, there's a way I can associate a 2 to 1 mapping as well. Fine, you do that. I can't stop you from doing that. Okay. But the definition of same size is this notion of one-to-one correspondence. All right, excellent. So we've now established that countable sets are, in fact, exist, and they are, well, we know they exist, but they're definitely different from finite sets in a very interesting way. Okay. Well, what about all the integers? Is z countable? Can you associate to z, which, if you remember, is infinite in both directions, can you associate to this a bijection that will put this in a correspondence with the natural numbers? How many people say yes? Some of you have seen that. You want to suggest one, Rebecca? Yeah, and let's not bother writing out the definition because it could be messy. Well, just tell me where to start. Let's call this one. How about calling this one 1? And then what? 2, 3, 4, 5, 6, 7. Now, do you agree that this pattern could be continued and that I could, if you force me to, write down a definition like that? Yeah, you probably just take care of the 0 first and then use some thing here that depends on whether the argument's odd or even. Okay. Excellent. So z, in fact, is countable. Oh, really? Okay. Z is countable. 2n is countable. The set of even integers is also countable. Can you see how to show that the even integers, minus 6, minus 4, minus 2, 0, 2, 4, 6, is going to be countable? Yeah, in fact, you could use this idea and this idea, a combination, right? Yes, question?
Can you just say if a set is a subset of a countable set, that it has to be countable?
Ooh. Excellent, excellent. Yes, you can. In fact, that's a theorem that we are about to show. Perfect segue. Awesome. Every subset, not every subset, but every infinite subset of a countable set is going to be countable. That's actually a very helpful lemma because it means that you can avoid doing some of these explicit constructions. So here's a theorem. Every infinite subset of, let's call it E, of a countable set is countable. So let's call the countable set A. Okay. Well, what's the basic idea? I'm just going to give the proof idea. It's written out carefully in the book. But what's the idea? The idea is, let's suppose that A is countable, so I will think of this as a sequence, x1, x2, x3, dot, dot, dot. And now I'm picked off various a subset of this. Maybe this is in the subset, maybe this one is, maybe this one is. Skip a few, maybe this one is, etc. Right? But not necessarily everything's in it. But it's infinite. What can I do? Your task now is to list the things in E. How will you do that? Well, sure, it'd be nice if I could pick off the first thing here, the second thing here, the third thing here, right? So if you take a look at what's happening in the book's proof, this is exactly what's happening. The idea is we're going to, let's let n1 be the first index that appears. So take the infimum of all the indices I such that x sub I is in E. That's n1. Why does this infimum exist? Why is it, what do you mean it's bounded below? Sure, real numbers can be bounded below, but not have a smallest element. This is a set of natural numbers. The natural numbers are well ordered, so a non-empty set has a least element. So this exists by the well-ordering principle for the natural numbers. Okay, you can pick the smallest thing. Now, once I pick off this index, that's the first thing in my eventual thing here. The first thing is x sub n1. What should x sub n2 be for my set E? What should x sub n2 be? It should be the next thing, which in this case is the third element of the original set. So that's what I want n2 to be. In this case, I want it to be n3. So what should I pick off? Steve?
Well, you could make it just the same definition as
Excellent. Let's demand that I be xi drawn from x sub all the x sub I that are in E, but now we'll demand that I be bigger than n1. Okay. And in general, you could demand that n sub k be the same definition and demand that it's bigger than everything preceding it. Okay. And then we have a listing for E. This is the idea. Okay. Happy with that? Beautiful. So this lemma actually will become very, very useful. Because the next question we want to answer is, let's see, we've shown the natural numbers and lots of interesting subsets of them are countable. We've shown the integers are countable. And in fact, then, any subset of integers is countable by this theorem, yes? Good. So what's another set you know of that's likely not going to be finite, and we wonder if it's countable? The rationals. Are the rationals countable? Q. Is it countable? Why is Q countable?
Because I can make a way to count
Okay, so let's call this a theorem. Q is countable. All we have to do is produce a listing. Okay? And in fact, I'm going to do it the following way. I'm going to write the rationals, if you don't mind, as ordered pairs. Okay? So the ordered pairs, I'll just start with, in fact, I'm just going to do the positive rationals, and you can deal with the negative rationals by using that trick. Okay? But let's just say 1 over 1, 2 over 1, 3 over 1, 4 over 1, dot, dot, dot. Yes? And now I'll do 1 over 2, 2 over 2, 3 over 2, 4 over 2, etc. And then the next row I will do 1 over 3, 2 over 3, 3 over 3, 4 over 3, dot, dot, dot. Now, these are ordered pairs of numbers, yes? And if I want, and would you agree that every rational will appear in this array, this two-dimensional array somewhere? Yes? Every positive rational. Yes? So all I have to do now is list them in some order. Would you agree that if I do the following, I start here, and then I proceed diagonally through this picture, like so, zigzagging my way, that I will eventually hit everything in this grid, etc.? Yes? Now you should worry about something, because the way I've done this grid, some rationals what? Repeat. But why is that not an issue? Good. What we've really shown is ordered pairs of natural numbers are countable, and the rationals are just a subset of them where you pick one representative to be in this picture, right? You just skip over the ones that you don't care about, right? You don't care about this because it already appeared the first time. You don't care about this because it already appeared. 2 over 1, 4 over 2, you're going to omit. You can omit as many as you like. The whole thing is a countable set, so any subset is. Are you happy with that? Very, very nice argument. So let me point out, not only have you shown that Q is countable, but we've also shown the following theorem. If A is countable, then in fact, A cross A is countable. Yes? Yes. That's correct. Yeah, so this is actually a proof that Q plus is countable. But now, if I wanted to show that Q was countable, how could I do it? I'll use this trick. Put all the positive rationals going one way, the negative rationals going the other way. Yes? That produces a bi-infinite sequence, but that can be put in sequence by now picking 0 off first and then doing this thing back and forth. Are you happy with that? John has asked an excellent question. So the positive rationals are countable, and if you want to show that Q is countable, you can either use that trick, or if you like, I can use the listing of make one of these include the negative numbers, one of the numerator to the denominators, and list those in some order. Like, for instance, start this one with 1, 2, 3, 4 all over 1, and the next row with minus 1, minus 2, minus 3, minus 4 all over 1, and then proceed to denominators 2, 3, 4. Use smiley, and smiley is this trick. Okay. Excellent. Very good. Actually, more generally, the book shows this. Not only is ordered pairs countable, but ordered triples are countable as well, or ordered quadruples. Why? Induction. Okay. Excellent. Very good. So we have actually now that Q is countable. What's the next set we might worry about? Yes, are the real numbers countable? That's a question some of you know the answer to, and some of you, I realize, don't. So here's a question. Is R countable? Can you list all the real numbers? Now remember, if you want to show, if you think the answer is yes, you just produce a listing. If you think the answer is no, you have to show that any listing you try is going to fail to hit everything. Okay? With me? Okay. So, well, let's see. Maybe I don't know the answer. But if I were to, let's just suppose there were some listing. I don't really know if there is or not. Actually, I do, of course. But suppose there is a listing. Let's see if we might run into problems. So here's a proposed listing. Now notice this is proposed listing looks something like this. I don't know. Let's say the number 1 gets associated with some rational, and this one gets associated with some rational, 2, 3, 4. And maybe the rational looks something like this. I'm just going to, let's say maybe the first rational 1 gets associated with this number. Okay, that, of course. Okay, there. That's some rational, right? Okay. Some real number, excuse me. So here is n, and these are real. These are elements of R, so they don't have to repeat in their decimal expansion. Here's another number. How about maybe the next number looks something like this? Okay, I just made that number up. Okay. Maybe the next number looks something like this. And I will really make the rest of these up. Okay, etc. So here's a proposed listing, which has a bunch of numbers in it. So okay. So okay, so I'm not going to keep going, obviously. But now, I claim that, if you look at this list, I can produce a number on the right-hand side that isn't in this listing in a very special way. So in fact, here's the theorem. Is R countable? No. I claim it's not countable. Sorry, that's a funny theorem. The theorem of no. There are some assumptions. That's the answer to everything. No! Oh, interesting. Well, here's the idea. So it's a proof by contradiction that begins by assuming there is a listing. Suppose there exists a bijection. And, the best way to explain it is to look at this example. So, e.g., look at this picture here. Okay? Suppose there is a bijection that looks something like this. What I'm going to do, I will show the bijection is not really a bijection. That will give me a contradiction. Are you with me? I will show that the bijection, if you call this function f, I will show this bijection f is not onto. And that will be a contradiction. Do you agree that if I show it's not onto, then the proposed bijection is not really a bijection? And this will be a general proof that will hold for any proposed listing, not just the one I have here. Okay, I just have to show you what to do with any such listing, and I'll do it by example. Well, I'm going to produce a number, a real number, that doesn't appear anywhere on the list. And the way I'm going to do that is I'm going to make sure that it disagrees with every number in some decimal place. Okay? How will I do that? I will produce a number that disagrees with the first number in the first decimal place, the second number in the second decimal place, the third number in the third decimal place, the fourth number in the fourth decimal place, etc. Are you with me? And the way I will do that is I will look at the nth digit of the nth number, in this case the fourth digit of the fourth number, and if it is a 7, I will make it a 1. And if it's not a 7, I'll make it a 7. So my number might start off like this: 7, 7, 7, 1, 7, dot, dot, dot. So this proposed number, I'm going to call this x star. Let's call this x star. And the claim is x star is not f of n for any n. Do you see why? Why is this number that I've constructed, which I basically made different from every number on the list, not going to be on the list? Well, you say it that way, and it's obvious. Well, yeah, isn't it? Why? X star disagrees with every number that's on the list. Notice that x star, y, x star differs from fn in the nth decimal place. So it's not on the list. So it's not in the image. So x star is not in the image of f. Done. End of proof. Huh, beautiful. Interesting. We have a set that is somehow bigger than the natural numbers. It can't be put into one-to-one correspondence. Some people find that a little bit surprising. Surprising? Some of you find it surprising. Some of you have seen this already. Let me ask you a question. How come this proof does not prove that the rationals are uncountable or not countable? What goes wrong, Willie? Say again? Wouldn't necessarily be rational. Yes. Okay, good. So notice this proof would not work to show the rationals are not countable. Good thing, because we just showed that they were. But it doesn't work because that would demand that everything on the right side be a rational number. And yes, you could produce a number that's not on the list, but there's no guarantee that that number is rational, right? So it wouldn't disprove anything. Okay. Oh, very good. Okay, very good. So in fact, R is uncountable. And this leads to, and I'll just finish with this comment here, a notion of the size of sets. So really what we have here is we have sets of different cardinalities. So here's a list of some sets with different cardinalities. There's a set of size, there's all the J, J0, J1, J2. These are all the finite sets, right? But then we also have the natural numbers, which happen to be the same cardinality as Q, right? So this is the same cardinality as Q. They're in the same category. But then there's also the real numbers, which is not in the same category. Okay? Interesting. So there's a natural question you should ask yourself. Are there other sets of different cardinalities? Are there other things here? There's a question. Interesting. Here's a theorem. So the answer is yes, there are in fact tons of different cardinalities. In fact, there are infinite number of cardinalities. Is that countable or uncountable? It's uncountable. There's a lot of cardinalities, and here's a theorem. So for any set A, the claim is A cannot be put into one-to-one correspondence with 2 to the A, where the power set of A. What's the power set of A? The power set of A is the set of all subsets. 2 to the A is just a notation for the set of all subsets of A. And this is a theorem which you should try to prove it. I claim it actually uses a very nice argument. This argument here we used for the rationals can be reused here. Proof, it's a diagonalization argument. And I'd like you to try to think about this, and then I might tell you next time how you prove this. But it looks very similar. It's this this is called a Cantor diagonalization argument. And if you think this is somehow a bit surprising, you should know that it actually was a huge shock to mathematicians of the late 1800s when Cantor came up with his argument. People really scratched their heads and said, "What? Really? There are different sizes to infinite sets?" Yes, there are. And so the consequence of this particular fact is that, if you look at the set of all functions or graphs in the plane, set of all functions from R to R, that's a much larger size of infinite set than the real numbers, okay? Because it's basically a power set of the real numbers. So you can just keep going if you want. One other thing I should mention, I'll just mention this, is there is a question of whether there's a size of infinity in between n and r. You could ask that question. And it turns out that that question is is provably undecidable. Okay? So what does that mean? It means is you could take it to be the answer to that question to be true or false, and not violate the mathematics as we know it, unless mathematics itself has some inconsistency. Okay, so it's a rather surprising fact. That's called the continuum hypothesis. Okay, we'll see you next